All right, so last time we talked about the geometric series. This is the geometric series, and again, the terms, every term is r times the previous term, as you see, and we are adding this forever. So what we did is we found the partial sum. S sub n is the sum from the first term till the nth term. We found a formula for it. It's this right here. Okay, so a 1 minus r to the n, and here is how many terms you add over 1 minus r. And then we wanted to know when this thing has a limit. So if you're finding the value of the actual series where k goes from 1 to infinity, you take the limit of the partial sum. Here is the formula. Again, that limit is dependent on r. Okay, if r is a number between -1 and 1, then as n goes to infinity, this r to the n goes to 0. And this is what you end up with. So here again, note that for absolute value of r less than 1, or we say r between -1 and 1, r to the n goes to 0 as n goes to infinity. Okay, so for example, if you have 1/2 to the power of n, as n gets large, this goes to 0. And again, you end up with this thing right here. And if r is any number more than, r is any number not in this interval, then this limit does not exist. Okay, so to summarize, if we have a series that's geometric, this, let me write it in series form, k going from 1 to infinity. By the way, again, I can call this n instead of k, n going from 1 to infinity of a times r to the power of n minus 1. This is equal to a over 1 minus r for absolute value of r less than 1. The series would be convergent if the common ratio is between -1 and 1. Yep. So let's see if we could do an example. Yeah, so keep in mind what would happen if r is not in this interval. If absolute value of r is more than 1, then imagine r is 2. If r is 2, then this thing is gonna blow up. Okay, the terms get big and bigger. If r is equal to 1, this thing doesn't even exist. You have 1 minus 1, which is 0. Okay, it's undefined. And the series would be just a minus a plus a minus a, and so on if r is 1, and that doesn't have a sum. So just try out different cases for r and see what makes sense. Okay, so let's do an example. Let's say we have the sum. Let me go with k for now. K, N, I, J, M, L, doesn't matter. Okay, so here we have our stuff, a geometric series. All right, if you want to expand some terms, if you want to expand the sum for a little bit, be my guest if you want. So if I plug k in, k equal to 1 for k, then this becomes a negative 1/2 to the 0 power. That's equal to 1. 1 times 3 is 3. That would be first term. Okay, second term is when you plug 2 for k, you get negative 1/2 to the power of 1. That gives us a minus 3 over 2. Okay, if you plug k equal to 3, you get negative 1/2 to the power of 2. And negative to the power of 2 is positive, so we get 3 over 4. Okay, next term is going to be negative 3 over 8. Next will be 3 over 16, and so on. Okay, so as you see, every term is negative 1/2 times the last term. Okay, the series is, of course, geometric. All right, now, guys, does this converge or does it diverge?
Converge.
Yes, Colin, this is going to converge because the common ratio is equal to negative 1/2, and that number is between negative 1 and 1. Let me write that common ratio in a different color. Let's go with orange. And here A is 3. That is your first term. Yeah, so this is equal to A divided by 1 minus R. R here is negative 1/2. Okay, and if you simplify this thing, you're gonna end up with 2. You get 6 over 2. Is that right? Yeah, 6 over 3, that's just equal to 2. Okay. Yeah, or another, so we have convergent. Let's do another example. If you have,
So Professor, it converges because the R is between negative 1 and 1.
yes, I mean, we got 2.
Yeah.
The value of the sum is 2. Obviously, the sum exists. It's convergent. Let's say we have, and again, it doesn't matter if I call the index k, and let's call it n. Let's say we have 5 times 3 over 2. Oops, I meant to write that in orange. 3 over 2 is r to the power of n minus 1. Again, I call the index n. So let's expand this for a little bit. Here, first term is equal to 5. You don't need to expand. You don't need to. I'm just going to expand it a little bit so you can see what's happening to this series. First term is 5. And then second term is when you plug 2 for n, you get 3/2. So we get 5 times 3/2. Let me just leave it as 5 times 3/2. Okay, next term is going to be 5 times 9/4. Okay, next one will be 5 times 27 over 8. Okay, so as you see, those terms get big and bigger. Okay, because the common ratio is more than 1. This is not going to have a sum. Its value is infinity. Okay, this is divergent. Since absolute value of r is more than 1. Or you could just say r is more than 1. All right. Yeah. So geometric series have a lot of applications, as I said, a lot of applications. Finance, physics, what I mean, a lot. Economics, gambling, probability. One application of geometric series is to express numbers that are repeating. You've seen those numbers that are in decimal form and they repeat. The decimal doesn't terminate, but there's a pattern in decimals. Have you ever wondered how to convert from decimal to a fraction? Well, let's do one of those examples. So let's say we have a number, and let's go with, I don't know, 2.123 bar. Okay, so 2.123 bar is the same as really 2.123, 123, and so on. So 123 just keeps going forever. Okay. Yeah, this number is a rational number. You guys know what a rational number is. A rational number is a number that can be written in a fraction form. Okay, and decimal numbers that don't terminate are rational, and we can actually show that. We can write this as a fraction. Okay, so for part A of the problem, what we are going to do is we are going to rewrite this number as a geometric series. A lot of the famous numbers that you guys have seen in the past, like pi or e, they have a series representation. Well, pi is not a geometric series, but e, pi, those transcendental numbers have a series representation. Every number that is transcendental, like ln of 5, how does a calculator know how to calculate ln of 5? Guess what? They use a series. ln of 5, log of 27, let's say, e, pi, every number can be written as a series. Square root of 2 has a series representation, and calculators use series to come up with those values. And we're going to learn about pi, square root 2, square root 3, e later on. But for now, we can work with simpler situations. But 2.123, can be written as a geometric series because we can first of all write it as a series. We can rewrite this number as a sum, as 2 plus 0.123 plus 0.00. I have already written 3 decimals, so 3 zeros, 1, 2, 3 plus point. I have written 6 digits, so we'll just write 6 zeros, 123, and so on. Okay. Yeah, every one of these values, 0.123, 0.00123, can be written as a fraction. Okay, just leave the 2. This 0.123 is 123 over 100. I'm sorry, 1,000. Yes, that's 123,000. And then 0.00012 is the same as 123 over 1 million. Okay, I can actually write those. We can write those in powers of 10. Let me do that because it's easier. Okay, 1,000 is this. 1,000 is the same thing as 10 cubed. Okay, 1 million is the same thing as 10 to the power of 6. Next number is 123 divided by, let's see how many zeros. We have 3, 3, 3, so 9 zeros. You could write that as 10 to the power of 9, and so on. This is definitely a geometric series. Okay, well, 2 is not a part of the series. 2 is not, the series begins with this number. Because, so 2 is not a part of the series because I can't multiply 2 by number to get the next. Okay, so this is the first term of the series, and we can find the common ratio. Let me write it down. So first term is what we call A. A is just 123 over 10 cubed, or 123 over 1000. And the common ratio, well, just ask yourself, what do you multiply every number by to get the next number? Guys, what do you say?
123.
What?
123.
Well, okay, so if again, what do I multiply this by to get this? If I multiply this by 123, then I would have 123 squared.
Right.
1 over 10.
1 over 10, if I multiply this by 1 over 10, then I would have 1 over 10 to the power of 4.
1 over 10 cubed.
1 over 10 cubed, yes. Well, if you don't see that, if you can't get that by looking at it, just divide any 2 consecutive terms. That's what you could do. You could just do A2 divided by A1. Okay, or you can do A3 divided by A2, because that's the definition of the common ratio. Okay, here A2, yeah, this is let me open some room here. Yeah, this is A1, this is A2, that's A3, A1 is the same as A. So take A2, A2 is 123 over 10 to the 6, okay, divided by A1. Dividing is the same as multiplying by the reciprocal. A1 here is 123 over 10 cubed. So when you reciprocate, you get 10 cubed over 123. Okay, the 123 is canceled. 10 cubed over 10 to the 6 is 1 over 10 cubed. All right, and that is the common ratio. Okay, so remember, we did something like this earlier in the sequence section. Divide any 2 consecutive terms, or you could just think about it. I have to multiply this by a 1 over 10 cubed to get the next term. I have to multiply the second term by 1 over 10 cubed to get the next term, which is 123 over 10 to the 9. Okay, so since I know the first term and I know the common ratio, then I can write this number in a series form. Okay, so 2.123 bar, okay, is the same thing as 2 plus, again, 2 is not a part of the geometric series. So I just do 2 plus the summation. And again, you can use n or you can use k. And going from 1 to infinity of a is 123 over 10 cubed. That's my a, times r to the power of n minus 1. R is 1 over 10 cubed. Okay, remember, this is the general form of a geometric series. There we go. So that is our series representation. Don't believe it, but then start expanding it. Okay? Check. Plug 1 for n. If you plug 1 for n, this becomes to the power of 0, which is just 1. Okay, 1 times 123 over 10 cubed gives you 123 over 10 cubed. That would be the first term. Plug n equal to 2 to see if you get the next term. plug 2 in, you get 123 over 10 cubed times 1 over 10 cubed. That gives you 123 over 10 to the 6. Okay, but yeah, this is it.
Professor, I just have a quick question.
Oh, yeah.
I'm just confirming. So the value in front, the 123 over 10 cubed, that's just the first term, right?
This one.
Yeah, that one, yeah.
Yeah, yes, this is the first term of the series.
Okay, perfect. Thank you.
Yeah, because if you look at again, if you look at the way I have written down the series, yeah, it's A plus AR plus AR squared. Yeah, that A is the same as this A.
Okay.
And
perfect.
R is the common ratio. Okay, yeah, again, as I said, every number, every rational, irrational number has a power series representation. For instance, E is the summation of 1 over n factorial, where n goes from 0 to infinity. We're gonna learn that later. If you don't know what factorials are, that's okay. We'll learn about it later. Pi has a lot of different series representations. I don't remember the pi representation. But I guess I just remember E. You can derive the power series representation, the series representation of pi later on when we get to section 10, 10.6, 10.7, 10.8. But next part of the problem ask us to rewrite the number as a reduced fraction. Okay, so yeah, all I have to do is to use the formula for the sum of a geometric series to get basically the sum of the series. Let me also use some colors here. So this A is in blue, I guess. R is in orange. Yeah. So that's but basically what you're doing. So find the sum of the geometric series. This is how you answer the problem. Okay. Here we know this is A and this is R, and the sum is A over 1 minus R. All right, I'm gonna copy. Let me copy this down here. All right, so we have 2, leave the 2, treat the 2 differently. And then, yeah, since this is convergent, because of course the ratio here is less than 1, it's between -1 and 1. Then you just do A, which is 123 over 10 cubed, divided by 1 minus R. R is 1 over 10 cubed. And they want it in the reduced fraction form. So don't leave it like that. This is complex fraction. You want to get rid of those fractions within. So what you do is multiply top and bottom by 1,000. 10 cubed is 1,000. We'll multiply by 1,000 over 1,000. Again, this is to simplify. Okay, and we end up with 2 plus. On the top, we just get 123 because 1,010 cubed cancel. And the bottom, 1 times 1,000 is 1,000 minus, yeah, 1 times that gives you 1,000. 1 over 10 cubed, 1 over 1,000 times 1,000 is just 1. So we get 2 plus 123 over 999. Okay, and yeah, and we are done. Okay, so in mixed form, the number is 2 and 123 over 999. This is the mixed form, and this form is cool. It's a mixed number, but it is reduced because 123 over 999 doesn't reduce anymore. Don't believe it? Take your calculator, do 123 over 999. It gives you 0.123, Okay. So guys, try and see how this formula applies to finances. Okay, Google it, search it. It's the geometric series is used a lot in annuities. Okay, and annuity, you guys probably heard of compound interest. Yes, you have. Compound interest is when you put some money in a bank, in a savings account, you don't touch that money, you don't deposit, you don't withdraw, and it earns interest periodically. Okay, so like let's say after a year, you invest $1,000 in the bank. After a year, it earns 5%. So you have extra $50 after a year. Okay, so then you have 1,050 in the bank. For the second year, the bank will pay you interest on the 1,050, not on the original 1,000. That's compound interest. Okay, but of course, if you open a savings account or if you invest your money, you like a retirement account, you deposit money every once in a while, like once a month, you deposit $300, okay, in a bank for a certain number of years. That's called an annuity. An annuity is an investment that earns interest compounded on a compounded basis, and you make periodic payments. All right, and if you want to find the future value of an annuity, you have to use a geometric series. So you don't need to know this stuff for Math 8. We don't do annuities or finances, but try to see why. Try to see how you can come up with the future value of an investment of an annuity by using a geometric series. Okay, so we are done with geometric series. Let's move on to the next series. Guys, so we've seen the telescoping series and how to deal with it, how to find a formula for partial sums, take the limit, so we can get the value of the actual infinite series. We've seen geometric series. Okay, now we're gonna talk about the harmonic series. You guys know what a harmonic series is. 1 plus 1/2 plus 1/3 plus 1/4 and so on. But we have not yet discussed the convergence or divergence of the harmonic series. And that's what we're going to talk about. Okay, so again, just to remind you, the harmonic series is the sum, k or n, doesn't matter, 1 over k. K begins with 1. It can't begin with 0. 1 over 0, that would just make no sense. Let's see, Jose has a question. So an irrational number is a number whose decimal not only goes forever, but don't follow a pattern. That's correct. Yeah, square root of 2 doesn't follow a pattern. Yes, exactly. Yeah, if an irrational number had a pattern in the decimals, then we could exactly write it as a geometric series, but we can't. That's why irrational numbers are not geometric. When you write them in series form, it's not geometric. It still has a series representation, like the square root of 2 does still have a series representation. That series is not geometric. Okay, it involves factorials. And we'll get there again in chapter 11, section 11.7. So again, the harmonic series begins with 1 when you plug 1 for k, 1/2, when k is 2, 1/3, 1/4, and so on. The values go down. They go down by, well, they go down. Okay, when you let k go to infinity, this thing goes to 0. Okay, and we are adding a bunch of values that keep getting smaller and smaller. We want to know if this thing is going to converge. What are you talking about, Lexi? I thought he said you could.
I thought beforehand you said that you can write pi using a geometry.
Yes, you can.
But isn't it an irrational number?
Yes, it is. Okay, so it's irrational numbers can be written as a geometric series. Irrational numbers can still be written as a series, but not geometric.
Got you. Okay.
There are just different kind of series. Like E is 1 plus 1 plus 1/2 plus 1/6 plus 1/24. This is not geometric. Well, again, we're going to learn why E is that. But irrational numbers are numbers that in series form are not geometric. Okay. All right. So when we talked about the integral, remember the improper integral from 1 to infinity of 1/x dx. This thing diverged. It diverged. And again, a series is a discrete form of an improper integral. They don't have the same value. They're not the same things, but they kind of behave the same way. And that's what we're going to learn in section 11.3. We're going to talk about series using improper integrals. Okay, so we kind of do suspect that this thing is going to diverge. But back then, whoever working with the harmonic series, they didn't have the improper integral tool. They didn't know what integrals really were. Okay, or maybe they knew, but they just didn't know how to evaluate those integrals. So question is, how do we know if this thing is divergent or convergent? Well, there's a proof. There's a proof that, first of all, this thing, the theorem says that this thing diverges. You know what people did in the beginning to see if these diverge or converge? They added. They just sat down and they added term after term. Yeah. I told you guys the story of that girl who's taking an algebra test. But but the thing is that if you guys sit down and add, like imagine you can live as long as the age of this earth. So what would that be? Like 15 billion years? Yeah. Imagine you add the values of the series 4.5. Let's say universe, okay? Let's say you're as old as the universe, not Earth. So universe is born, you're born with it, Big Bang, all of a sudden, there you are, okay? And you're just sitting, I don't know where exactly. And let's just say that you have the most powerful computer. You have well, there are quantum computers right now, but let's say you have a really, really powerful, let's say the fastest computer, supercomputer, okay? And you add the terms of this series for, again, as long as Earth lives, 15 billion years. This sum is just going to get to 75 or something like that. Okay, it doesn't get big too fast. Okay, so don't rely on empirical evidence to see if this thing is convergent or not. If you have a, say I have a divergent geometric series. So here's a geometric series, like 3 times 5/2 to the power of n minus 1. If I add like 3 or 4 terms, I right away see that the terms get big. Okay, and the sum would therefore get big. But with this series, don't rely on a calculator or addition to see if the terms if the sum gets big and bigger. Okay, so no empirical evidence, but someone actually came up with the proof of this theorem without doing integrals, without adding terms. What they did was really, really clever. They took the power, they took the series and they kind of grouped the terms. Okay, they did it this way. Let me show you. Yeah, we'll look at the partial sum. So instead of me adding from 1 to infinity, we'll look at the partial sum. And then we'll see what happens to that partial sum as n gets big. So we'll do the partial sum, k from 1 to n of 1/k. This is equal to 1 plus 1/2. And again, I am gonna group terms. So next 2 terms, I write them in blue, 1/3 plus 1/4. All right, next group, I'm gonna write them down in green, 1/5, and you'll see why I am grouping it this way. 1/5 plus 1/6, 1/7 plus 1/8. Okay, so this group has 4 terms in it. Next group, I'll write it down in red. Okay, and this group is going to have, so look at, I want you to notice a pattern. The blue group has 2 terms. The green group has 4 terms. Can anybody just guess for me how many terms in the next group? Just guess. 8. Wow, what a good guess. Yeah, 8. So we'll go with 1/9 plus 1/10. And I'm not going to write every number because it's going to take long. So last is 1/16. Yeah, this one has 8. Next group is going to have 16 terms. It would start with 1/17 plus 1/18 all the way to 1/32. Okay, and this thing goes forever. You know what? Let me just, instead of doing a partial sum, I'll just do an infinite sum here. We'll keep it simple. Yeah, we'll do an infinite sum. Okay, so this goes forever. All right. Yeah. So let's see what is so special about every one of those groups. Okay, here I'm gonna do some work. Let me see. Let me cut and paste this onto the next page. Yeah. All right. So yes, let's see what is special about every one of those groups. Let's go with the blue group. 1/3 plus 1/4. We can say that every one of these numbers is greater or equal than 1/4. Okay, just believe me for a second. Here I can say 1/3 is greater than 1/4. Okay, just ignore 1/4 for a little bit, guys. Ignore 1/4. We know that 1/3 is larger than 1/4 because the denominator of 1/3 is smaller. Okay, so if I add a 1/4 to both sides of the inequality is still true. 1/3 plus 1/4 is more than 1/4 plus 1/4. Just think about that for a second. If A is more than B, that implies A plus C is more than B plus C. Adding the same number to both sides of an inequality still holds true. So again, here 1/3 is more than 1/4. So if I add 1/4 to both sides, the inequality is still true. On the right-hand side of the inequality, we have 1/4 plus 1/4, which is the same as 2/4. And 2/4 is equal to 1/2. Okay, so this group, the blue group, is more than 1/2. Let's look at the green group. Green group is 1/5. Okay, we can do exactly the same thing with this group. We can say that each one of these is more than 1/8. 1/5 is more than 1/8, and you'll see why in a second. Plus, I can say 1/6 also is more than 1/8. Same goes with 1/7. 1/7 is more than 1/8. And just add a 1/8. The inequality still holds true. Okay, you have 4 1/8. When you add them, you get 4/8, which happens to also be 1/2. A green group is also more than 1/2. Okay, we can also use the same reasoning to say that the red group is more than 1/2. So here it goes. The red group is 1/9, 1/10, all the way to we have 1/15, 1/16. Okay, we can say every one of these numbers is more than 1/16. Okay, and since we have 8 of them, 1/9 through 1/16, there are 8 values, then that group is more than 8/16, which is also half. Okay, so your 1/9 is more than 1/16. 1/10 is more than 1/16. Every number in between is more than 1/16, including 1/15. 1/15 is more than 1/16. In addition to 1/16. And again, here we have 8 of them. Therefore, we have 8/16, which is, again, 1/2. Okay, so this way, again, this way we can show that every group is more than 1/2. Okay, therefore this series is more than 1 plus 1/2. Okay, the blue group is more than 1/2. The green group is more than 1/2. The red group is more than 1/2. And how many times am I adding 1/2 to itself, guys? This thing goes forever. I'm not done with the groups. This is dot, dot, dot. Again, next group goes from 1/17 to 1/32. So it'll be 1/2 plus, I can just group the numbers forever to be more than 1/2. Right? So how many 1/2s is being added to itself? We have infinitely many 1/2s being added, which is the same as infinity. Okay, 1 plus infinity, that's infinity. So what we just showed is that the harmonic series is larger than infinity. All right, and if anything is larger than infinity, then that thing has to be infinity itself, right? Anything larger than infinity is got to be infinity. All right, just think about that, guys. Something larger than infinity has to be infinite itself. Okay, so we have divergence. Okay, what do you mean the proof would be valid if I do it with partial sums? I don't get it. This thing goes, well, this is an infinite sum, right? So I'm just adding the 1/2s forever. We haven't proved regrouping is allowed. Why not? Doing partial sum, proving partial sum would be a little bit more rigorous. Definitely more rigorous, because you could get you can try to come up with a description of the partial sum, take the limit of that, but I don't see why this is not allowed. Guys, does this make sense? I hope. All right, so that's the harmonic. The harmonic series is divergent, period. That's it. Okay, you don't need anything, any other analysis. We have also the integral test that we're gonna learn in section 11.3, the integral test. You can also use integrals to prove this is divergent, but we just proved divergent, so it's it. Okay, that is the harmonic series. We have the next type of series to look at, the P series or the hyperharmonic series. Let me see. Oh yeah, I can't introduce P series yet. I have to do that in the next section. Okay, but yeah, that's it. So telescoping series, geometric series, and the harmonic series. Okay, those are the 3 series that we've had to learn in section 11.2. There are a couple of things in section 11.2 that we need to know for sure. There is a very, very important theorem. Okay, this theorem, guys, is extremely important. Okay, because this theorem can be used to show certain series to be divergent. Okay, the theorem says that if you have a convergent series, let me call it a sub n, where n goes from 1 to infinity. If this thing converges, you guys have no idea how important this theorem is. If you have a convergent series, then, and this is just common sense also, then the terms of the series get smaller and smaller. Just think about it. Think about it. If a series is convergent, then the terms of the series must get smaller and smaller and get close to zero. The limit as n goes to infinity of a sub n is equal to 0. Okay? Yeah. Again, this says that if a series is convergent, then its terms get smaller or get closer to 0. Because if they don't, imagine the terms of the series don't get close to 0, then the sum is just gonna add up and get big and bigger. All right. We can prove this theorem by doing a contrapositive. We can do a contrapositive proof. Okay, or let me write the consequence of the theorem for you. Okay, the contrapositive of this theorem says that if the limit as n goes to infinity of a sub n is not equal to 0, if the terms don't get smaller and smaller, then the series diverges. I am restating the same theorem. This and this statement are the same thing. Okay. The consequence is just a contrapositive. You negate the conclusion, the hypothesis, and you switch them. It's the same thing. Okay.
What is a contrapositive?
Contrapositive, what?
What is that? A contrapositive?
Yeah, contrapositive is when you switch the when you negate the conclusion and the hypothesis and you switch them. Okay, contrapositive says this: if A then B, if A then B, the contrapositive of if A then B is if not B then not A. That's a contrapositive.
Okay, that makes sense. Thank you.
Yeah, switch, negate, switch. You're right. P and Q is are the letters I should be using, but that's a contrapositive. Okay, which again, guys, this is just intuition. We can prove this. Like imagine. So this is not a rigorous proof, but it will do. Imagine that the limit is not 0. It's equal to some number L, and L is not equal to 0. Okay. Then if you look at the series, so n goes from 1 to infinity of a sub n, this will be, let's say, approximately equal to a1 plus a2 plus a3. If this goes long enough, if it goes long enough, then every term is going to get closer and closer to L. So you have L plus L forever. You're adding a bunch of L to itself infinitely many times, so you get infinity, which is divergent. All right. So again, if a series is converging, then its terms should get closer and closer to zero. Let me show you an example. Let's say we go with 3n over n plus 1. This series. All right. Let's take the limit of the limit of the nth term, the limit as n goes to infinity of a sub n, which is the limit of the 3n over n plus 1. Well, this limit is just 3. 3 over 1, that is equal to 3. Okay. Well, this means that if I add the more and more terms I add to the series, those terms are going to get closer and closer to 3. Approximately equal to, or I should say equal to. I don't like the equal notation. This is the end behavior of the series. It's the end behavior. That thing means end behavior. Okay. Yeah, this is not an equal sign. This is the end behavior sign. All right, so if I write out a bunch of terms beginning n at 1, when you plug 1 for n, you get 3 over 2. When you plug 2 for n, you get 6 over 3. When you plug 3 for n, you get 3 times 3, 9. 9 over 4. Plug 4 for n, you get 12 over 5. But when you run the series long enough, then every term is going to be really close to 3. And you're eventually adding 3 to itself forever, and that is infinity. Therefore, you have divergence. Okay, so again, common sense, guys, common sense. And this consequence right here is your first test. As I said, we have tests. In chapter 11, we're going to learn about tests that will tell us if series converge or diverge. We have the integral test, section 11.3. We have the comparison tests, section 11.4. We have the ratio test. We have the root test. We have a bunch of these tests. This is the first of the tests. This is called the nth term test.
Professor, going back to the last one, we couldn't use the LH rule, right?
We can't use what rule?
The LH, the L'Hopital.
Oh, to get the limit? Yes, you can.
Yeah, that's what I thought. Okay.
Yeah, 3 over 1, that's 3.
But then that would be divergent.
Right. Well, the limit of this thing is equal to 3. Okay. But when you look at the series, you're adding these 3s forever.
Yeah, okay. That's what confused me a bit. Thank you for clearing that up.
Yeah, guys, make sure you're not confused. The limit of the terms of the sum is not the same as the limit of the partial sum. Please be careful. Yeah, so this is called also the divergence test. Test for divergence. And of course, it says that if, again, I'm writing this down, if the limit as n goes to infinity of the nth term, that's why they call it the nth term. You find the limit of the nth term. If this limit is not equal to 0, then we know for sure that the series is divergent. If the terms of the series don't go to zero, then the series is divergent. Okay. So example. Let's go with 2n squared plus n over, let me just write that again. Over n squared plus 1. Here we have ourselves a series. And the question, guys, by default is to determine if the series converges or diverges. That's the question by default. You can go crazy with this series. You could go nuts. And you can do integral tests that we're going to learn later. You could do comparison tests that we'll learn later. You can just do all sorts of analysis on it. But the nth term test should say that the series is divergent, because when you take the limit of the nth term, here the nth term is 2n squared plus n over n squared plus 1. That's equal to what? It's equal to 2. Again, you can do L'Hopital rule. But the top is a polynomial, bottom is a polynomial. You can just, since the degree is the same for top and bottom, you can just take the ratio of the leading coefficient, 2 over 1 is equal to 2, or you can use L'Hopital rule if you want. Okay, you end up with 2. And this 2 is not equal to 0. So guys, listen, please listen. Last thing we'll say here. So when you add the terms, when you write the sum out, okay, when you write it out, after a while, the terms are gonna be all very close to 2. And you're gonna be adding 2 to itself forever, which gives you infinity. Therefore, the series is divergent. I did not get 0. Okay, and again, this theorem, this test says the series is divergent. By the write down y. You just say by the nth term test. Okay. So a very good test, a very good way to check quickly and see if the series is divergent or not. All right, and we'll continue tomorrow.
Yeah, I have a quick question. So, can this be applied to like a geometric series or no?
Yes, it can be. Yeah.
Right? Like, cause
Yeah, if you have a geometric series, like let's say 3 times 5 over 2 to the power of n minus 1, when you do the limit of that, limit 3 times 5 over 2 to the n minus 1, the limit of the nth term, this limit is equal to infinity because 5 over 2 gets big and bigger, right?
yes.
And that's not equal to 0, so the series is divergent.
Oh, okay. Yeah, because I was looking, I was like, wait, because it didn't like it's not specified whether or not you can use it for like any series. So
Any
basically,
series, you
any
can use it
series,
for
right?
any series, yeah.
Even for harmonic, geometric, and for
No, okay, guys. So I must mention here, and we'll talk about this more tomorrow. If this nth term test works for series whose nth term don't go to 0, if if the limit of a sub n is equal to 0,
Mhm.
if the limit is 0, then the nth term test doesn't say anything. And that's what we have to be careful about. If the limit of a n is 0, then the series could diverge, could converge. We don't know.
So it's
Okay.
either or.
Yeah, it's either or. I need to discuss that tomorrow. Make sure you guys don't make that mistake. Okay, but we'll talk about it tomorrow.
So Professor.
Yeah.
If it equals to 0, then we can't use this test. We have to
We
find a
can't-
different way.
Yes, exactly. We have to choose a different test.
Wait, but then in the theorem, like it's mentioned that if the series converges, then the limit approaches 0. Oh, you're saying it the other way around. If the
Yes,
limit
that's the other way around.
Oh, so if the
If-
limit
if-
approaches 0, then it's
Yeah.
either or.
Right. If A implies B, then we cannot say that B implies A.
Oh my God.
It's not a two-way statement, it's just a one-way thing.
Okay.
Okay, but yeah, well, so again, if you're not understanding what we are talking about, we're gonna talk about this in details tomorrow because I want to make sure you guys don't make a mistake of using this test when the limit goes to 0. When the limit goes to 0, we cannot say convergence because
Okay.
anything could happen.
Okay.
Yeah, I had a, let me pause. Yeah, you can do all problems, Jose, in that section.